stack PSP start is nothing but stack MSP end. Let me write an inline assembly code. Here, when we enter main, let's change SP to PSP. Let me call this function. The first step, what we're going to do in main is change SP to PSP. And I'm going to implement that as a naked function because we just want to use some assembly instructions. That's my goal. I cannot write it as a C function. I'm going to use attribute void change SP to PSP. First, let's initialize the PSP. ASM, volatile. What is the instruction? MSR. Syntax is special reg you have to mention first. PSP and the register RN. I'm going to use R0. But what is the value of R0? R0 is not initialized. Let's initialize. ASM, volatile, LDR, R0 equal to, let's initialize that with PSP start. That's great. PSP is initialized now. After that, use the control register to change the SP to PSP. It is right here. Control register is another special register of the processor. So this is also not memory mapped register. So it doesn't have any address. That's the reason we have to again use inline assembly code to access this register. In this register, you have to change the first bit position. You have to make it as 1. PSP is the current stack pointer. Defines the currently active stack pointer. We have to make it as PSP. Let's do that. I'm going to again use ASM, volatile. I'm just going to use move instruction here because, see, I cannot use move instruction here because this is a 32-bit value. If you want to use move instruction, then the immediate value has to be 16-bit. Here, I can use just immediate value of 0x02 because I'm going to set the first bit. And after that, ASM, volatile, MSR, control R0. That's it. This code is going to first initialize PSP and then change the SP to PSP. After that, let's write one more function called generate exception. We will cause some exception. Let me implement that function. Void generate exception. I'm going to use SVC instruction to trigger the SVC exception. If you don't know about SVC exception, then don't worry. It is one of the exception of the ARM Cortex-MX processor. We are going to cover that later in the separate section. SVC instruction can be executed by the thread mode code in order to get some services from the kernel level code. It is basically used in an OS environment where your application involves separate kernel code and user code. SVC is the instruction which is used to implement the system call layer. We'll see that later. We'll understand the syntax and other things later. But for a time being, let me use this SVC instruction with an immediate value of, let's say, any value between 0 to 255. When thread mode code executes this, SVC exception will be triggered in the processor and the SVC exception handler will be called. Let's write the SVC handler. The name of the handler you can get from here, SVC handler. Let's go back to the main.c and let's implement somewhere here. SVC handler in SVC handler. Let me just debug this code. We have a problem here. I think I cannot use the C macro in an assembly instruction. I think That is not allowed. No problem. We can do one more trick here. Instead of using C pre-processing macros, we can use equal assembler directive. This is a syntax. You have to use the assembler directive EQU followed by the label, comma, the value. So it is just like a similar way of creating macros. Let's use that. So I'm going to write ASM volatile EQU. Let me give the label SRAM end. First, let's calculate the SRAM end, which is nothing but, let's open the parenthesis, 0 cross 2 0 0 0 0 0 0 0 plus 128 in 2024. This is the SRAM end. According to our calculation, what is PSP start? PSP start is SRAM end minus 512. That's it. After that, use PSP start here. All these are not required. That's it. I'm going to compile this. There is some problem. Here is the problem. I didn't close this. I have to close this parenthesis. Now it looks good. Fine. Let's test this. Here we call change SP to PSP in the main function. So the control reaches here. And we should go back to the main function. That's why we have to now use the return instruction. The return instruction is BXLR. BX stands for branch indirect. When we jump from here to here, the LR is the register which captures the return address. LR knows where to go back when this function finishes. That's why we have to use LR here. The content of the LR will be copied to the PC, which is nothing but the return address. That's how control comes back to the main function from change SP to PSP function. And let's debug. Let's do single stepping and open the disassembly, or I can open the registers. Here first load R0, and here it is. The value of R0 is something like this. This is our start of stack for thread mode code. After that, that value is getting placed into PSP. You can see that PSP value is also modified here. PSP carries this value. After that, we are going to switch SP to PSP. What is SP? SP is still pointing to the MSP, remember that. Now we do a switch. Here it is, SP value got changed. So now PSP is used as SP. That's the reason why PSP value is copied into SP here. You are returning back to the main. Let's execute this instruction and you reach main. SP value is still same, no change. And after that, generates an exception. This code actually generates an exception. Let's do that. Let me execute SPC instruction and observe this SP. Execute this, and here it is. SP value is now changed to MSP. Because handler mode code always uses MSP. That's why the processor does that change automatically. When you leave this handler and you go back to the thread mode, again SP will start using PSP. You can see that. So here it is. SP is now started thread using PSP. That's a demonstration of using PSP in thread mode and MSP in handler mode, and changing the default stack pointer from MSP to PSP. As I said, most of the standalone code doesn't need this switching. It's not at all required. You can do everything using MSP, need not to switch to PSP. But for some OS designs, or when the application is involved with kernel code and thread mode code, then the OS design uses such techniques. So now let me conclude this lecture with summary. Let's have the summary of MSP and PSP. Remember that physically there are two stack pointer registers in Cortex-M processors. First one is main stack pointer called as MSP. This is a default stack pointer used after reset and is used for all exception interrupt handlers and for codes which run in thread mode. And we have one more stack pointer called process stack pointer PSP. This is an alternate stack pointer that can only be used in thread mode. It is usually used for application tasks in embedded systems and embedded OS. Remember that after power up, the processor automatically initializes the MSP by reading the first location of the vector table. And about changing SP to access MSP and PSP in assembly code, you can use the MSR and MRS instructions. Never write C program, a pure C program, to change the value of PSP and MSP and to make a switch. You have to use naked functions, remember. In a C program, you can write a naked function that is a C-like assembly function which doesn't have epilogue and prologue sequences to change the currently selected stack pointer. In the next lecture, I'm going to cover function call and WPCS standard. I will see you in the next lecture. Hey, welcome back to the lecture. In this lecture, let me cover function call and WPCS standard. WPCS stands for ARM Architecture Procedure Call Standard. Let's consider two functions here, function X and function Y. Function X is calling function Y. In this case, function X is called as caller and function Y is called as callee. The callee function, that is function Y, also receives four input arguments from the external world or from some other function. And the function Y also returns a data back to the caller. These terminologies, that is caller and callee, are used more oftenly in this standard. This is a document actually, you can get it online. This WPCS standard describes procedure call standard used by the application binary interface for ARM architecture. You will understand why it is required. Let me explain in next slide. So very importantly, the WPCS defines how subroutines can be separately written, separately compiled, and separately assembled to work together. It describes a contract between a calling routine and a called routine that defines obligations on the caller to create a program state in which the called routine may start to execute. Obligations on the called routine to preserve the program state of the caller across the call. The rights of the called routine to alter the program state of its caller. This standard acts as a rule or specification when multiple people are developing multiple assembly routines and all those assembly routines finally go into one single project. Then all must adhere to one specification. When a C compiler compiles code for the ARM architecture, it should follow the WPCS specification to generate code which involves caller and callee. According to this standard, a C function can modify the registers R0, R1, R2, R3, R14 and PSR, and it's not the responsibility of the function to save these registers before any modification. For example, let's say there is a function y. In this function, you want to modify R0 or R1 or R2, something like that. The caller has some important data in R0, R1, and R2, let's say. In function y, you are modifying that. And caller needs that values after this function call to do some other job. But the function y modifies that. So the specification says that it is not the job of the function y to save these contents. That is the job of caller. The caller should push all these registers to the stack and after that pop it back when the function returns. That's what the standard says. I hope you get that point. If a function wants to make use of R4 to R11 registers, then it's the responsibility of the function to save its previous contents before modifying those registers and retrieve back before exiting the function. Let's say this function wants to modify R7. Then it first have to push R7, then modify R7, then pop R7 before exiting the function, so that when the control goes back to the caller, the R7 value must be intact. It should not be corrupted. These have to be followed if you are writing a function or a subroutine in pure assembly language. But if you are using C program, then you need not to worry at all. Why? Because compiler generates instructions. Compiler will follow these standards. A C program writer need not to worry about this. R0, R1, R2, R3, R12, R14 registers are called caller saved registers. It's the responsibility of the caller to save these registers on stack before calling the function if those values will still be needed after the function call and retrieve it back once the called function returns. Register values that are not required after the function call don't have to be saved. R4 to R11 are called callee saved registers. The function or subroutine being called needs to make sure that contents of these registers will be unaltered before exiting the function. And remember that according to this standard, caller function uses R0, R1, R2, R3 registers to send input arguments to the callee function. The callee function uses registers R0 and R1 to send the result back to the caller function. Consider here a function, and this function x is calling function y, isn't it? When the function y is being called, 4 arguments are being passed to the function y, and the function y receives those arguments on its local variables. These are the local variables of function y. According to this standard, always these 4 registers are used to pass the arguments from one function to another during function call. What function x does is it copies these values into its internal registers R0, R1, R2, R3, and function y copies the registered contents back to its local variables. That's how arguments being passed from one function to another during the function call. When this function y, if it wants to return the result, then it will always use the register R0. It copies the result to R0. If the result is 64 bits, then what happens is 2 registers being used, R0 and R1. So the higher 32 bits will go here and the lower 32 bits will go here. That's how result is returned back to the caller. But what if the arguments are more than 4? What if it is 5 or 6 or 10? Function y sends 6 arguments.